Recording is rolling. It is Friday, January 12th. So we haven't quite done textbook puzzles yet. So end of the week, good opportunity. I think way I want to do with you guys is read the questions with you guys, go over how to do the solutions. You guys have the solutions printed on your desk, and then hopefully there's a good amount of time where you guys can independently work on these, which is probably a good way to do it and help each other out. It's like the best way to learn. Of course, you guys have AP Classroom Unit 6. Hey, guys, everybody look here. Due on Tuesday morning. Yesterday, I was helping you guys out a bit because I was looking over it myself, and I think these formulas here should get either all the questions or pretty close to all the questions where you should be able to solve with just those right there. There's a lot of conservation of energy type questions. There were some Hooke's law related questions. I think there was one question about like pushing ice cube in the water and it like oscillates up and down. So that's like oscillatory type motion. Okay. And then yeah, we got a 3-day Martin Luther King Day weekend coming up. All right, so let's jump in here. All right, I just want to read these and help you guys set these up, think about them. And hopefully you guys have some good spare time here. Block with mass, so many kilograms attached to a spring with force constant, 130 Newton per meter. All right, so okay, so spring constant, how stiff is the spring? Free to move on a frictionless horizontal surface. Right? Oh, that's a pretty common setup, right? A frictionless surface. The block is released from rest after being stretched. Capital A equals 0.13 meters. So that could be an amplitude, right? Amplitude. Right? So that's a displacement. I might call that X, but it's like a maximum X. So a lot of times they just call that capital A for amplitude. Right? At that instant, find the force in the block and its acceleration. Okay, so does that sound like Hooke's law, F equals kx? And then if you want to figure out acceleration based on force, well, that sounds like Newton's second law of motion. Okay? You see that right in the solutions. There's Hooke's law, there's Newton's second law of motion right there. Number 2, spring oriented vertically attached to a hard horizontal surface. All right, so you see that in the diagram. They give the spring constant of the spring. How much is the spring compressed when an object with that mass placed on the spring and the system's at rest? Right. So how much is it compressed when it's at rest? You guys, at rest, does that sound like, do you guys think something to do with forces in equilibrium or something to do with conservation of energy? What do you think? Like it's just hanging out at rest? Yeah, that's equilibrium. So we're going to do the forces. So I think that's also going to be Hooke's law, right? Also, I think you have to know the weight of this thing. They told you the mass, so you think it's probably implied that you're on Earth, right? You have to also use that, right? So Earth gravity field. Right, let's take a look. Oh yeah, right there's Hooke's law again, right there for number 2. Right, number 7. Do the circled one, just like normal. Spring, so many meters long with a spring constant, so many newtons per meter, hanging from an elevator. Okay, I'll pause right there. The fact that they give you the length of the spring, I'm pretty sure it's not going to be useful. I haven't read the question yet, but a lot of times it's extraneous information, so it doesn't really matter how long the spring is, right? As long as it doesn't. Right. Okay, block okay with this mass attached to the bottom of the spring. Okay, so again, probably have to assume Earth gravity again. That probably matters. Right? Just like last question. How much does the spring stretch when the block is slowly lowered to its equilibrium point? Okay, slowly lowered to its equilibrium point. That is also Hooke's law, right? F equals kx, something like that. I think there's mg pulling straight down, and there's kx holding it up, and those are going to be in equilibrium. Okay, let's look at the solution. I just want to look at the setup, and ideally, you guys should be able to solve this all from scratch on a blank piece of paper. Yeah, there we go. Got kx and mg balancing out. Ooh, maybe I could have written that a little bit better, but right. Some version of Hooke's law again. Right. By how much is springs? Okay. If the elevator subsequently accelerates upward at 2 meters per second squared, what is the position of the block? All right. So it's gonna be a few parts of physics. Okay, remember elevator physics? I guess we can make this more or less complicated, but the sort of shortcut version is if you were standing outside that elevator and the elevator is accelerating up at 2 meters per second squared, and Earth gravity is about 10 meters per second squared, to you it feels like you're in a gravity field. How strong? Yeah, 12 meters per second squared, right? So you're like 10 plus 2 meters per second squared, right? Now, if this was an FRQ, you wouldn't want to just jump to that. They'd want to see, you set up a free body diagram, you do a setup, and you prove that's the case, right? But kind of a shortcut, that would be the where you go, right? So now what's the equilibrium position? Okay, well, I bet it's going to stretch more, right? It's kind of like it has this sort of added weight effect. If the elevator cable snaps during acceleration, describe the subsequent motion of the block relative to the free falling elevator, and what's the amplitude of its motion. Right? So this is kind of like going back to number one. Right? Number one, it was a horizontal orientation. You pull the block, some amplitude, and you let go. It's going to oscillate back and forth. Well, inside an elevator, just turn this vertical, right? Okay, now it's got some weight that's going to cause some initial displacement, right? And then if you cut the elevator cable, right, so this whole thing goes into free fall, right? That's kind of like if you turn gravity off. Oh, let's just like turning this back horizontal, right? And is it just going to oscillate, right? As if there's no gravity field, right? Something like that. Yeah, so it would just oscillate at that point. When you look at the solutions, I bet you'll see that story. Right, number 11. Child's toy consists of a piece of plastic attached to a spring. The spring is compressed so many centimeters. Toy is released. The toy has this mass. Notice they gave it to you in grams. You have to convert to kilograms. Probably got to get guys. Pretty fun way. Trying to help you guys out. Right. And rises to maximum height of so many centimeters. I think you probably want to convert to meters. Estimate the force constant of the spring. How stiff is the spring? Right. Guys, does this one sound like Hooke's law with forces in equilibrium, or does this sound like conservation of energy with spring energy turning into gravitational potential energy? Yeah, I'm thinking conservation of energy. This would sound like, right? Look at the solutions. I bet. Let's see. They find the solutions real fast. I bet this is a conservation of energy setup. Let's see, number 11. Oh, there it is, right there. This kind of energy turned to that kind of energy. Boom, just like that. Right, number 13. A 10-gram bullet. Okay. Again, right off the bat, they gave you not base SI units. Convert that to kilograms before you do any math on that. Okay? Fired into, embeds in a so many kilogram block attached to a spring with a spring constant of so many newton per meter, and whose mass is negligible. That's one of those little details that you see all over the place. The fact that springs themselves might have very, very tiny mass compared to, say, blocks and bullets that are interacting with them. Right? So that the idea is like if you're considering conservation momentum, right? Which I think you have to do with the bullets fired into the block. You guys remember ballistic pendulum from last semester? Ballistic pendulum. Right? So let's think back to ballistic pendulum because I think this is a similar concept. Right? The idea was a bullet was fired into the block. There was a collision there. There's conservation momentum, and then the whole system swings up to some height. There's a height change. There's conservation of energy. So it's like a two-part problem. Right? A lot of times you solve that backwards. Right? Okay. So I'm thinking the same thing here. I'm thinking there's a collision here. You have to do something with conservation momentum. That's good. Unit 5 review. Right? Okay, and then we got a spring. Okay. How far is the spring compressed? Yeah, this does sound a lot like that ballistic pendulum, except instead of being a pendulum, now we got energy going into compressing a spring. Probably something to 1/2 kx squared. Okay. They gave you the speed of the bullet. So the fact they gave you the speed of the bullet and the initial speed of the bullet looks like you can actually solve this forward in time, right? Right? We usually hand a ballistic pendulum backwards. Right? See, notice you must use. Oh, hey, they even give you a hint here. Look, they said use conservation momentum because of the collision, right? Inelastic collision, right? So I think it's going to be. Oh yeah. All right. So I see the solutions right here. Right? Part 1, part 2. Conservation momentum for the collision. Conservation of energy for squashing the spring. Boom, just like that. That's it. Right? And see if you can solve it from scratch. Right, now, number 19. I should tell you guys. I did not actually print the solutions in number 19. Long story there, but I'll help you guys out here. Outdoor market, bunch of bananas attached to a vertical spring with the spring constant right here. So many newton per meter, set to oscillatory motion with an amplitude of so many centimeters. Right? I want to convert to meters. More math with that. It is observed that maximum speed of the bananas is 40 centimeter per second. What's the weight of the bananas in newtons? Right? Because that's how you quantify weight in the SI system, right? Newtons. Right? And so this one I did not write the solution. So let's take a look at this right here. We got, say, spring. I got a dish full of bananas, something like that. Okay. And what do they say here? We got some spring constant they gave to you. It's K. Right. You guys write this down? You guys writing this down in your notes? Okay. We got this oscillatory motion. Right. So it's bounce up, down, right? Where they gave you an amplitude. So I'll call that capital A. Now, you might call that X, right? Like some displacement, but I'll call it capital A for like the maximum displacement. You can call it X max if you want to. and they gave you the maximum speed. So, guys, do you think the maximum speed is as it's going through this equilibrium position? Do you guys think that's the location of maximum speed? Call it Vmax, right? Something like that. You're saying, right? Right. Now, I could tell you the reason I don't have the solution written is back a few years ago when I was originally putting this together, I was thinking, well, wouldn't you have to consider some kind of gravitational effect, its weight, because it's vertically oriented? Yeah, I spent like a couple hours, I think, on that. It was like really messy and it wasn't really coming together. And then I looked up and realized, okay, actually, I told you guys this earlier this week. It doesn't matter the orientation of spring, whether it's vertically or horizontally oriented. Mathematically, it's going to work out exactly the same. Okay. So maybe I could do a conservation of energy, I'm thinking. Right. Do you guys think and just ignore Earth as part of the system. So I could call this the banana spring system. Okay, I'm just going to leave the Earth out. So I'm not even going to consider gravitational potential energy. Okay, something like that. So I might do sum of energy initial equals sum of energy final. Okay, at some point the spring has maximum stretch. That's 1/2 Ka squared, right? And at some point, the bananas have maximum speed, in which case that's going through the equilibrium point, and the spring would be, you could consider the spring to be not stretched. You might say, well, isn't actually stretched because it's vertical. That's another thing you can kind of cut through, right? So yeah, if you hang it vertically, then at the equilibrium point, it would be stretched. We're going to be treating that as if there's not stretched at all. It's kind of weird. Anyway, so going through the equilibrium point, we're going to consider all the energy to be kinetic. So you got 1/2 mv max squared. Right? And what do they want us to solve for? They gave us what is the weight of the bananas in newtons, right? So okay. I bet if you solve for mass, then you can just multiply mass by gravity field and you could get the weight that way, right? Okay. So let me double check. You should have these other three things. They give you K. Yeah, I'm seeing a K they gave you. They gave you the amplitude, check. And they gave you they gave you the maximum speed, check. So check. Okay, so you got those other three variables. Can you guys do that? To solve for that? Right. Yeah. Right. Because you could make that a wildly more complicated problem, but that's it really just boils down to that. Right. That's what it does. Right. Okay. Number 34. Man enters a tall tower needing to know its height. Notices a pendulum from the ceiling that's has a time period of that's a huge time period, right? I bet that's a Foucault pendulum, right? I know if you go to if any of you attend University of South Florida or University of Central Florida, they have Foucault pendulums that are like several stories tall. They have like these huge shafts in these like science buildings. Watch them swing back and forth. Might take like 15, 16 seconds to swing back and forth. Okay. How tall is the tower? If the pendulum's taken to the moon where there's less gravity field, then what's the time period there? Right. Do you guys think this is time period is 2 pi square root L over G? And then you can, in this case, solve for L. Right. Here's the time period of a pendulum, solve for L, right, so like that, right? Okay. Right. And then you can do part B if you take out to the moon. Here, let's do a conceptual version of this. Guys, if you go from Earth, where it takes like, it's called about 15 seconds to swing back and forth, and you go to the moon, where there's a lot less gravity, on the moon, it's going to take many more than or many less than 15 seconds to swing back and forth. How about many more than, right? Because if you decrease the gravity field, that's going to correspond to increasing the time period, right? There's an inverse type relationship there. Right. Number, actually here, I'm going to do these last two backwards, right? Number 66, because number 66 is real straightforward, right? Got so many grams block. I want to convert that to kilograms, as I thought. Released from rest slides down a frictionless track, which is, has a 2-meter height drop. Is the fact that they give you a height change and the surface is frictionless, that's all flags for what type thinking, what past unit. I'm thinking, yeah, conservation of energy, right? Conservation of energy, right? Oh, okay. Notice they didn't even give you the angle of the slope, right? You don't know, is this a 30-degree angle or a 50-degree angle? It's ambiguous, right? It could be either. So like a kinematic type approach, like, well, you could have all different lengths here and all different angles, but in terms of energy conservation, all you care about is this height change, right? There's no frictional loss there. Right? At the bottom of the track, the block strikes and sticks to a light spring. Light spring, again, the idea being negligible mass, so you don't have to consider conservation momentum during the collision. Guys, this block colliding with the spring, when you see collision, the first thing you should think in physics, oh, something to do with conservation momentum. But exception here, the fact that the spring has negligible mass, light spring, means you don't do any kind of conservation momentum. No conservation momentum, right? Okay, but they told you how stiff the spring is. Find the maximum distance the spring is compressed. Guys, whenever you're trying to find the maximum compression, that's different than equilibrium compression. That's especially if you see like something hanging vertically or oscillating vertically, right? You'll get different answers from different approaches. If there's some kind of equilibrium compression you're looking for, that's something to do with Hooke's law and dynamics, F equals kx kind of thing, right? But if you're looking for a maximum compression, that's not Hooke's law, that's not dynamics. That's also what part of physics? Conservation of energy. Right, there you go. Right, so there's conservation of energy all over the place. Let me find the solution. That's number 66. I bet it's conservation of energy. Where? Oh, here it is. Here. Oh, yeah. It's real short. Half a page right here. Conservation of energy. Boom. Just like that. That energy turns to that energy. All right. And last one. There's an oscillation graph you're supposed to describe with an equation. Number 42. Right. Ooh, do you guys see x versus t? Right. Displacement versus time. Now it looks like, just look at this graph. The fact that it starts at the origin. The way I've been teaching you guys, I've been giving you an initial displacement, like you initially displace something and then it goes into motion naturally, right? Here they have it starting from the origin, which is kind of weird. It's probably already in motion, or maybe somebody like came along and like bumped it with a hammer or something, and boom, set it in motion. One or the other, something like that. I bet you could describe this with a sine or a cosine. What's actually a better fit? The fact that it starts at 0, 0. Yeah, sine is more straightforward. You could describe it with like a shifting cosine, but yeah, probably a sine graph is a more straightforward way to describe that mathematically. For this motion, find the amplitude. Let's just, guys, what is the amplitude of this? 2 centimeters, 2 centimeters. There you go. Amplitude is 2 centimeters, right? If you had to describe the energy stored in the spring at the maximum stretch point, 1/2 kx squared, probably convert that to meters first. Guys, how many meters is that amplitude? 0.02 meters. Yeah. Right. Oh, see the time period, guys. What's the time period? 4 seconds. I see one full S shape, 4 seconds it takes to cycle, right? Oh, see, angular frequency, isn't that 2 pi times the regular frequency? Guys, what's the regular frequency? The time period is 4 seconds. So what's the regular frequency? Yeah, 0.25 hertz, right? 1/4 hertz, right? And so the angular frequency is just 2 pi times that, right? Which is going to help you craft this equation later on, right? The maximum speed. Ooh, well, if we're converting back and forth between like a stretch and speed, here, where does the maximum speed happen? Is that at time 0, time 2, time 4, time 6 are the maximum speed points, right? I think that actually is exactly one of your AP classroom questions, if I remember, right? Right. So at those times, 0, 2, 4, and 6, as long as there's no energy loss, which is shown here, 0, 2, 4, and 6 seconds, the maximum speed happens, right? But you could solve conservation of energy. I think I would use to solve that, right? Maximum speed, conservation of energy a bit, right? The maximum acceleration. Ooh, maximum acceleration. Does that correspond to maximum force? I'm thinking F equals ma, probably something to do with Newton's second law of motion, right? And at what times is there a maximum force and therefore maximum acceleration? How about at 1 second? I see a maximum displacement. So F equals kx, right? I bet there's maximum force and therefore also maximum acceleration, right? Also time 3 seconds and time 5 seconds, right? So 1, 3, and 5 seconds, there's maximum stretch, maximum force, maximum acceleration, right? If you made the velocity versus time graph, that'd be the rate change of this. This would be 0 velocity right here. And then if you took the derivative of that and found maximum acceleration, then this would be, well, also back to maximum value for acceleration. Yeah. I think it'd be like down here something. Right? And find an equation for position in terms of, okay, so x as a function of t as a sine function. Okay. course, you have the solution written out, but see if you can do this from scratch and then use this to check your answer. Okay, I'm thinking I'm going to use this right here as a model for for displacement as a function of time, right? If you find velocity as a function of time, it looks like this, right? So there's a bunch of little steps involved in this one, right? So I got chain rule going on here. It's a little calculus crossover, but if you're in calculus a bit, you can definitely figure this out from scratch, right? If you're not, you might need a little bit of help here, right? There you go. Who's got any questions so far? Any questions so far? All right, great. We got about 15 minutes in class left. I definitely want to give you guys some time to work independently. So yeah, pull up blank paper, see how many of those you can knock out, and remember you got AP Classroom due on Tuesday, and we'll go over the answers to AP Classroom on Tuesday.